Now that you're a master of electron configurations, or at least I hope you are, now we're going to talk about orbital diagrams. So orbital diagrams are very similar to electron configurations, so don't freak out. They show the placement of electrons in an atom. So instead of just showing us how many they have, they're going to show us exactly where they're going to be located. And we use boxes to represent the different orbitals. S is going to have one orbital, which we'd represent with a single box. P has 3 orbitals, which is represented with 3 boxes. D has 5 orbitals, represented with 5 boxes. And F, which remember is our 2 rows at the very bottom, has 7 orbitals. A little trick I use to remember how many boxes I need to draw: it's half of whatever the number of elements would be in that orbital. So for example, our s orbital has 2 elements in each. 2 divided by 2 is 1. Our p orbital has 6 elements that make it up in each row, so 6 divided by 2 is 3. That's how I remember how many boxes to draw, but you can come up with your own way. The energy level and sublevel are written under the boxes. So example, you would write 1s or 2p. And electrons are represented with arrows. Only 2 arrows per box, and they will be pointing in opposite directions. Now there are 3 rules or principles that are used when drawing orbital diagrams. The first one is the Aufbau principle, and the Aufbau principle states that electrons occupy orbitals of lower energy levels first. Basically saying we don't just automatically start in 3D, we have to start in 1s, and then to 2s, and then to 2p. We have to go from the very beginning first. Hund's rule says that in a set of orbitals, the electrons will fill the orbital in a way that would give the maximum number of parallel spins, meaning they want as many electrons to be unpaired as possible. A great analogy for this is think about riding the school bus. In most cases, students fill up the school bus taking seats individually before people start sharing seats. It would be totally weird to have half the school bus empty, but then half the students jammed into the front half of the school bus. That's not how it works. So we want to put individuals in boxes first before we start pairing them up. And then there's the Pauli exclusion principle, and that states that an orbital can hold only 2 electrons and they must have an opposite spin, meaning you're going to have 1 arrow going up and you're going to have 1 arrow going down. So let's do an example together. Let's draw the orbital diagram for nitrogen. So first thing you're going to do is write out the configuration for nitrogen. And you should write it out as 1s2, 2s2, 2p3. A pretty simple one. Then you're going to draw the boxes you need and you're going to label them. So s orbitals only get 1 box, so we draw our 1 box and put a 1s. We draw our second box and put a 2s. And then the p orbital gets 3 boxes, so we draw 3 boxes and put 2p underneath them. Then we're going to fill in our arrows following Aufbau's, Hund's, and the Pauli's rules. So we are going to fill in our lower energy levels first. So we fill in our 1s, we put in our up arrow, we put in our down arrow. We fill in our 2s, we put in our up arrow, we put in our down arrow. Then when we get to 2p, it is 2p3, meaning we need 3 arrows. And you put 1 arrow in each box facing upwards. Why are there arrows in 2p in separate boxes? It's because of Hund's rule. We're saying that they want to maximize parallel spin. These are all parallel to each other. So we fill up all one direction of arrow before going back through and putting in the other one. Got that? I hope so, because now it's time to practice. I want you to pause this video and I want you to try drawing the orbital diagram for boron, drawing the orbital diagram for bromine, and drawing the orbital diagram for titanium. Pause this video, seriously, pause it. Try these on your own and then come back to check your answers when you're done. All right, let's see how you did. Boron was a pretty easy one. Similar to nitrogen, we have our 1s2 filled up, our 2s2 filled up, but this time we still draw all 3 boxes of 2p, but only the first box gets one up-facing arrow in it. Bromine is a big one. I put it in this kind of vertical format to save myself space, but if you wrote it out all on one long line, that's not a problem. You'll notice that every layer got filled in with 2 in each until we got all the way to 4p. And you should have had 4p5 written down in your electron configuration, so I went 1, 2, 3, 4, 5, leaving that one arrow all by itself. Your last orbital diagram was for titanium. This was a big one. Titanium got into the 3D level, and since it is 3D2, we put those 2 up arrows and left the rest of it completely blank. How'd you do? If you got this down, great. If you're not sure how I got the answers I got, come into class with questions tomorrow. So a few more things we want to talk about to finish up. And those are electrons and energy levels. So electrons and their energy levels are considered to be what is called their ground state. If electrons are given extra energy, they can actually jump up in energy levels. So go from that level that they're currently at to a higher level. We call this the excited state. When they fall back to their original energy level, they release a photon of light. A photon of light is a tiny particle of light. And the color of the light corresponds to the amount of energy the electron released when it goes from its excited state to its ground state. And this all relates to the electromagnetic spectrum. And that's the range of wavelengths or frequencies over which electromagnetic radiation extends. So we have our different types of waves. We have radio waves, microwaves, infrared waves. In the center, we have our visible light, the rainbow, Roy G. Biv. Then we get to our ultraviolet rays, our X-rays, and our gamma rays. We can't see any of these. We can only see the visible light in the center. On this end, we have our low energy waves, so radio waves being our lowest. And as far as colors and the visible light are concerned, red is our lowest visible light energy color. All the way up to our high energy, gamma rays are the highest kind of energy, and our blue, indigo, purple is our highest energy color. The same goes for frequencies. This end we have our lower frequencies, while this end we have our higher frequencies. And wavelength, maybe a little different than what you were thinking, but our long wavelength is over on this side, with radio waves having the longest wavelength and red having the longest wavelength of the visible color spectrum, and gamma rays having our shortest wavelength, and this end of the color spectrum having the shortest wavelength as well. We're going to be talking more about these interesting colors in an upcoming lab. So come ready to class with any questions that you have.